Hello everyone, this is the solution to Quiz3 here. Now the task was to develop the function getMaxTau, and the input arguments were magnitude, phase, and omega of GS basically, and we know that we are going to add some delay tau to the system in a unit feedback structure to end up in marginal stability. Now let's first of all create a script or function that is called getMaxTau. So function, and our input is magnitude, phase, and omega here. We're going to return the value tau. Now let me also create a main file here to run this. Clear CLC. Let's define a transfer function here. That is basically 10, 1, 2, 3, maybe. So now the first thing that we need to extract here is the magnitude, phase, and omega values of this transfer function. So call body here, gs, and then squeeze mag, or you can just skip it and do it in the function here to be safe. So let me basically do that. So this part is not really important. I am just going to squeeze it anyways in the main function when I test your code. But yeah, we could also be safe like this. So then we're going to call this function here. And then we need to basically check for the result where we have TS, the closed loop here, which is going to use feedback. And then we have GS times TF 1,1, and then IO delay of tau, comma 1 here, because it's a unit feedback. And we could maybe check if the step function behaves like we think it should. So before I go into this part here, let's actually try to code this function here. So now it is important to note that this is the dual problem of getting a p-type controller, or this finding the stability bound of a p-type controller, because here when we are using a p-type controller, we are adding a gain to the system. Therefore, we look up the phase of the system. When we are adding some delay tau, then we're basically manipulating the phase of the system. Therefore, we should look for the gain of the system. And the stability condition was basically the following. If we are using a p-type controller, we know that the stability condition looks like k times d omega should be 1 and minus 180 degrees here. But if we are adding tau, then what we're doing is we're adding x minus j tau omega, like this. So it has basically no effect on the gain here. Therefore, actually this should be it without these lines here. So if we look at it, this has no effect on the gain. So we can conclude that the gain is going to be equal to 1. So we're searching for gain equals 1. But at that frequency, we're going to look at the argument of the system minus tau omega should be basically 180 degrees, negative 180 degrees here. So that's basically what we're looking for. So if we would solve this for the p-type controller, if we're looking for the gain, that would be basically the gain margin here. We're looking for the phase margin. So let's actually implement this. You can see that in line 11, we've written down that the gain of the system should be equal to 1. So what we're searching for is the following. At which frequency is the gain equal to 1? Because if the gain is equal to 1, we are halfway there for the instability condition, where the gain should be equal to 1 and the argument should be negative 180 degrees. So since we're adding only an argument to the whole structure, we cannot manipulate the gain. The gain should be equal to 1. So let's start with searching for gain equals 1 and at which frequency this happens. So how can we do that? Well, I used this actually in the laboratory sessions. So I'm looking for 1 minus mag. If this is minimum, then, or if it's 0, ideally, then at this index, we will have basically what we want. So error here. Now, what we can do is we can just check if the absolute value mag index, or 1 minus mag index, is less than 1e minus 2. So we could check that. Because we're searching using this minimum operator here, we're not sure if this is basically satisfying what we want here. The value here in the minimum function, this val here, can be different than 0. So it has to be 0 if we're looking for the tau value, the exact tau value that we're after. But it could be the case that that's not available on the gain plot of the given body data, then we cannot speak of a tau value because it would be incorrect. We're looking for an exact value or an approximate with this tolerance here, where magnitude should be equal to 1. So I'm interested in the phase value at this index here, so phase index, and then I'm going to say theta d, or something else, I'm just calling it like that, minus 100 minus phase val. So what I'm basically trying to do here is I'm trying to see what the phase margin is. This is basically the phase margin. Because I'm subtracting this value here, let's assume that our phase index value is 120 here. Then what this would do is it would add 120 to this, and we would get basically 60 out of it, or actually negative 60 here. And this negative 60 is basically our phase margin at this point. And we're interested in theta here. Actually, theta d is in degrees, so we could actually convert it into radians, because tau is going to be in radians, because theta is going to be omega times tau, and there's also a negative sign here, and omega is in radians per second. So we should adjust the omega value here. So theta equals theta d times pi divided by 180. So there we go. Now the tau value here is going to be equal to minus theta divided by omega index, because that's the omega value that we have. Now we can actually also display maybe the magnitude here, since we're in the testing stage here, string magnitude. You can repeat this for phase. This should be magnitude index, of course. And then phase index, and maybe omega star, which is going to be omega index. And we could also look at theta here. This is just for debug purposes. So theta is going to be theta, and there we go. Now let's see if it's working or not. we have that. Let's see. The main. We can see that the magnitude is 1.0098. The phase angle is negative 140 degrees almost, and this happens at 3.23 radians per second. The theta desired, or the theta d in degrees actually, is probably 180 minus 139. And when we convert it into that, we can see that it should basically hold. So let me also show that theta in degrees and theta in basically radians here. One more time. There we go. It's minus 40 degrees. That corresponds to minus 0.71. Therefore, when we divide it into 3.23 and getting rid of that, tau value is quite small, like 0.22 here. Yeah. So let's get rid of this debug here. Or actually, let's leave it there, but if it's not going to hit this, we are not going to see it. So yeah. When we drop these theta values here, we can maybe take this part and show it here. So that makes more sense now. Because I want to demonstrate the fact that we might end up in something here, but that might be incorrect. Now, if I copy the system and if I get rid of this, I guess it should be it. So let me run the main function here. First of all, we can see that the magnitude is 0.35, the phase is minus 45, omega is equal to 1, but the magnitude is not equal to 1. So that was the reason why I implemented this safety mechanism here. And you can see that it throws an error where tau is not assigned because we're in this else statement. We couldn't find a magnitude that corresponds to 1, but that is important for us. It should be satisfied with a certain tolerance here. So if that's not the case, then we are not able to come up with a finite tau value that causes this marginal stability in a unit feedback. Because the body gain plot does not go through gain 1, so therefore we can add as much as the delay as we want to the system. We cannot come up with a marginal stability point. So what should we do? Well, the easiest solution was to just assign it to none or inf and get rid of this issue here. If I do that, let's call main. There we go. It's just displaying the data, but tau is basically not a number. So let me get rid of this part here. And let me comment this out. And let's see what the step response looks like when we have the amount of delay calculated by our function. Takes quite some time. And there we go. We can see that the amount of delay is causing us problems. Now, if we reduce it a little bit, like times 0.95, what is the issue here? Let's see. Let's run it. There we go. We can see it is on the stable side. Of course, it is. It has a very low damping ratio, therefore we have high oscillations, but we can see that this value actually corresponds to the marginal stability point. If we add this much amount of tau, we can see that it's basically on the boundary here. Now, if we try it with the half amount of delay, then we can see this is basically the behavior. So we're on the safe side. We can use this much where delay for the system and it still stays stable. at this point. Now this is the end result here. You can see it's not that long. And the basic idea is to search for one, and of course to come up with the minimum value here, but it might be the case that it's not equal to 1. It could maybe find the value 1, so we should check for that. Once we've done that, we're just looking for this conversion here. Of course, the important part is to note that during this conversion, we need to basically take into consideration that theta here is in degrees, because the body plot is in degrees, the phase plot there is in degrees. And if we're looking for the tau value, omega is in radians per second, then tau should also be in radians. Therefore, the theta here should be in radians. So that's the important part. This could be a trap, and this one here could be a trap, but other than that, it's quite straightforward. And I'm not quite sure, but there are, I guess, MATLAB functions like margins or stuff like that that can calculate you basically the stability margins, the gain margin, the phase margin. We were interested in phase margin here. So if it was margin, I guess, yeah. Something like that. We can basically calculate it here. So yeah, this was of course forbidden. You can see if we provide it like that, it will give us the margin of the transfer function that we're interested in. And it again shows here, I guess, the gain margin is infinity, the phase margin is 40 degrees. You can see that we found 40 degrees and it is at 3.25. That was also our omega value, the approximate value that we came up with, I guess, somewhere here. There you can see those are basically almost the same numbers here, and we can see it kind of works. What happens if we update our transfer function to this one here? Let's also maybe test that out. So you can see the gain margin is infinite, the phase margin is also infinity. So you can add as much as delay to the system. In the unit feedback, you won't see marginal stability or instability. So that was actually it. Hope that this was helpful. Yeah, see you around.